Welcome to Section 5, Lesson 2. In the previous lesson, we defined a function as a rule that assigns exactly one output to each input. Today, we add the notation that makes the input-output structure explicit and lets us work with functions efficiently in algebra, calculus, and applied math. The notation f of x with the function name f and the input variable x in parentheses is universal across mathematics, science, and programming. It looks like multiplication of f times x, but it is not, and recognizing the difference between the two readings is the central conceptual move of today's lesson. We also walk through the evaluation procedure, which is exactly the substitute and compute workflow from Section 2 applied to a named function rather than to an unnamed expression. First idea on the board. Function notation writes a function as f of x equals some expression in x, with the f naming the function and the parentheses signaling that x is the input variable. The notation fx equals 2x plus 5 says f is a function whose rule takes an input x and produces the output 2x plus 5. Other common function names include GHF and capital letter symbols specific to a discipline like P for population or V for volume. The function name is just a label. The rule is the expression on the right side of the equal sign. Second idea. To evaluate a function at a specific input value, replace every appearance of the input variable in the expression with the specific value wrapped in parentheses and then compute using PEMDAS. The procedure is identical to the evaluation we covered in Section 2, Lesson 4, with the only structural change being the function notation wrapper. f of 3 with the rule f of x equals 2x plus 5 becomes 2 times 3 plus 5, which equals 11. So f of 3 equals 11. The notation also doubles as a label for the resulting numerical value, often used in further calculations. Third idea. Function notation is universal across mathematics, programming, and applied science. In every field where a quantity is computed from one or more inputs, the function notation makes the input-output relationship explicit and enables compact reasoning about the relationship. In code, function calls look like f open parent x close parent and behave exactly like the algebraic notation. In physics, formulas like P of t for population at time t use the same convention. Today we lock in the notation and the evaluation procedure with two clean worked examples, and the rest of Section 5 and beyond uses the notation continuously. Function notation writes a function as f of x equals some expression involving x, where f is the function name and x is the input variable in parentheses. The notation makes the input-output structure explicit and is universal across mathematics, programming, and applied science. The function name f is just a label. Other common names include GFP, V, and discipline-specific symbols. Here is the warning that comes with the notation. The expression f of x looks like multiplication of f times x, but it is not. The parentheses indicate function application, not multiplication. F and x are not separate factors, rather f is the name of a rule and x is the input passed into that rule. Reading f of x as f times x is the single most common beginner error and produces meaningless arithmetic when you try to manipulate the expression. Step 1 in evaluation. Identify the input value at which to evaluate. The notation f of 3 says evaluate at input 3. The notation f of negative 2 says evaluate at input negative 2. Whatever value sits inside the parentheses next to the function name is the input value to use in the substitution. Step 2. Substitute the input value into the rule, wrapping the value in parentheses to protect signs and exponents. If the rule is f of x equals 2x plus 5 and the input is 3, the substitution gives 2 times the quantity 3 plus 5. The wrapping parentheses are essential when the input is negative, because they protect against sign errors during the subsequent computation. Step 3. Apply PEMDAS to the substituted expression to compute the output. 2 times 3 plus 5 equals 6 plus 5 equals 11, so f of 3 equals 11. The notation also serves as a label for the resulting numerical value. The symbol f of 3 refers to the specific number 11 in this case, and can be used in further calculations as if it were just the number 11. Here is the first worked example. Given the function f of x equals 2x plus 5, find f of 3, f of negative 2, and f of 0. 3 evaluations, 1 per input, all using the same rule and the same procedure. Step 1. Evaluate f of 3. Substitute x equals 3 into the rule. Replace x with the quantity 3 in parentheses. F of 3 equals 2 times the quantity 3 plus 5. Compute 2 times 3 equals 6 plus 5 equals 11. So f of 3 equals 11. Step 2. Evaluate f on negative 2. Substitute x equals negative 2. Replace x with the quantity negative 2 in parentheses. F of negative 2 equals 2 times the quantity negative 2 plus 5. Compute 2 times negative 2 equals negative 4 plus 5 equals 1. So f of negative 2 equals 1. Step 3. Evaluate f of 0. Substitute x equals 0. Replace x with the quantity 0 in parentheses. F of 0 equals 2 times the quantity 0 plus 5. Compute 2 times 0 equal plus 5 equals 5. So f of 0 equals 5. Step 4. Collect the 3 evaluations. F of 3 equals 11, f of negative 2 equals 1, f of 0 equals 5. The function maps 3 different inputs to 3 different outputs through the same constant rule. Notice that f of 0 gives the y-intercept of the line y equals 2x plus 5 exactly 5, because evaluating at x equals 0 is the same as setting x to 0 in the slope-intercept form. Step 5. Verify by checking that the function is well defined. Each input produced exactly one output, no input had multiple outputs, and the rule was applied identically to all 3 inputs. The function definition checks from the previous lesson are satisfied, confirming f as a valid function. So the 3 evaluations are 11, 1, and 5. The big lesson from this example is the mechanical evaluation procedure. Substitute the input wrapped in parentheses, apply PES, read the output. The procedure is fast and reliable. The same procedure handles any linear function, any polynomial, and any rule built from arithmetic operations. Practice the procedure on 20 different evaluations and the workflow becomes automatic for the rest of the course. Here is the second worked example. Given the function f of x equals x squared minus 4x plus 1, find f of 2, f of negative 1, and f of 5. The rule is quadratic rather than linear, but the evaluation procedure is exactly the same. Substitute, then apply PIMDAS. Step 1. Evaluate f of 2. Substitute x equals 2 with parentheses. F of 2 equals the quantity 2 squared minus 4 times 2 plus 1. Compute 2 squared equals 4, 4 times 2 equals 8, 4 minus 8 plus 1 equals negative 3. So f of 2 equals negative 3. Step 2. Evaluate f of negative 1. Substitute x equals negative 1 with parentheses. F of negative 1 equals the quantity negative 1 squared minus 4 times the quantity negative 1 plus 1. Compute carefully the quantity negative 1 squared equals 1, 4 times negative 1 equals negative 4, but with the leading minus sign we have minus negative 4 which equals plus 4. So f of negative 1 equals 1 plus 4 plus 1 equals 6. Step 3. Evaluate f of 5. Substitute x equals 5 with parentheses. F of 5 equals the quantity 5 squared minus 4 times 5 plus 1. Compute 5 squared equals 25. 4 times 5 equals 20. 25 minus 20 plus 1 equals 6. So f of 5 equals 6. Step 4. Collect and interpret. F of 2 equals negative 3. F of negative 1 equals 6. F of 5 equals 6. Notice that 2 different inputs, negative 1 and 5, both produce the same output 6. This is allowed in a function because each input still has only one output. The duplication is on the output side, which is fine. The pattern is consistent with the quadratic graph having a parabolic shape that can hit the same y value at 2 different x values. Step 5. Sanity check. The 2 inputs negative 1 and 5 are equidistant from x equals 2. the apparent symmetry axis of the parabola from the quadratic structure. Both producing the same output is consistent with that symmetry. The verification confirms the evaluations are arithmetically correct. So the three evaluations are -3, 6, and 6. The big lesson from this example is the careful sign handling on a negative input plugged into a quadratic. The parentheses around the substituted -1 are essential to protect the squared term from becoming wrongly negative. Without them, students sometimes write -1 squared and get -1 instead of +1, which propagates as a sign error through the rest of the calculation. The parenthesis habit from section 2 lesson 4 pays off again here. Always wrap substituted negative values. 3 mistakes that catch every algebra student during their first weeks of function notation work. Each one is fixable with a small explicit habit applied on every problem. First mistake, reading f of x as multiplication of f times x and trying to manipulate it as a product. A student looking at f of x equals 2x plus 5 thinks f is some unknown variable and writes equations like f equals 2 plus 5 over x by trying to solve for f. The reading is wrong. F is the name of a function rule, not a variable, and the parentheses around x indicate function application, not multiplication. The fix is to read f of x literally as the value of f at input x, never as f times x. Saying the words out loud while reading the notation cements the correct interpretation. Second mistake, forgetting to wrap a negative input in parentheses during substitution into a rule with squared or higher power terms. A student evaluating f of -2 with the rule f of x equals x squared writes -2 squared and computes -4 when the correct value is +4 because the square of -2 is +4. The fix is to always wrap the substituted value in parentheses, especially when the rule has any squared, cubed, or higher power terms. The parenthesis habit from section 2 carries directly into function evaluation work. Third mistake, substituting the input only into one occurrence of the variable when the rule has multiple occurrences. A student evaluating f of 3 with the rule f of x equals 2 plus x squared writes 2 times 3 plus x squared, replacing only the first x and leaving the second x as a variable. The correct substitution replaces every occurrence of x with the input value, giving 2 times 3 plus 3 squared, which equals 6 plus 9 equals 15. The fix is to scan the rule for every occurrence of the input variable and replace each one with the input value before any computation begins. Function notation is one of the most universal pieces of mathematical notation in all of science, engineering, and computing because it cleanly expresses the input-output structure that pervades quantitative reasoning. 4 broad sectors below. In physics, position as a function of time is written p of t, velocity as a function of time is v of t, energy as a function of position is E of x. Newton's second law, force equals mass times acceleration, is sometimes written F of m and a equals m times a, with 2 inputs to a single function. The function notation framework makes the input dependence explicit and lets physicists reason about how outputs change as inputs change, which is the foundation of all of dynamics. In programming, function calls in every language use the notation f open paren x close paren, with the function name followed by the argument list in parentheses. The semantic match between mathematical function notation and programming function calls is exact same inputs always produce the same outputs. No input has multiple outputs. The function name labels the rule. Programmers who internalize the mathematical notation move faster on coding work, and mathematicians who internalize the programming convention move faster when implementing algorithms. In statistics and probability, the probability of an event A is written P of A, treating P as a function from events to numbers between 0 and 1. Probability density functions are written f of x or p of x and give the relative likelihood of the random variable taking the value x. Cumulative distribution functions are written f of x. The notation pervades every statistical calculation and every machine learning model. In calculus, the derivative of a function f is written f prime of x or df over dx, with the f prime notation being a derived function evaluated at x. The integral notation integral of f of x dx sums function values across an interval. Both the derivative and the integral are operators that take a function and produce a new function, and the notation makes the operator structure clean and unambiguous. The function notation skills you build today are the literal first step into all of calculus and into every quantitative discipline that uses calculus. 3 things to take with you from this lesson today. Function notation is one of the most universal and powerful pieces of mathematical notation, appearing across every quantitative field in the modern world, and mastering the notation now pays off across every later math class and every quantitative profession. First, function notation writes a function as f of x equals some expression in x, with the f naming the function and the parentheses around x signaling the input. Other common names include G, HFP, V, and discipline, specific symbols, but the structure is the same name followed by parenthesized input followed by the rule. Recognizing the structure on any equation tells you immediately that the function evaluation procedure applies. Second, to evaluate a function at a specific input value, substitute the input wrapped in parentheses into the rule and apply PEMDS. The procedure is identical to the evaluation work from Section 2, Lesson 4, with the function notation wrapper providing the function name and the input variable. Always wrap negative substituted values in parentheses to protect signs and exponents during the computation. Always replace every occurrence of the input variable in the rule, not just the first one. Third, fluff(x) is not the same as f times x, despite the visual similarity. The parentheses indicate function application, not multiplication. Reading the notation as a product is the single most common beginner mistake and produces meaningless arithmetic when you try to manipulate the expression. Train yourself to read f of x literally as the value of the function f at input x, with the words at separating function from argument. Coming up next, the lesson called Domain and Range, where the set of allowed inputs to a function and the set of all possible outputs of that function get formal names and rules. Domain and range are foundational concepts for the rest of Section 5 and for all of the function work in calculus,